So today we're going to be talking about logarithms. So logarithms are going to be a new topic for most of us. And so it's going to be really important that we follow along carefully. We review kind of anything that we're not quite sure on, or we ask for clarification or any questions that we might have. It's also going to be really important that we do all of our homework and practice problems with logarithms because, like I said, since we've never seen these before, it's going to take a little bit of extra practice to get used to them and get the hang of them. So our first thing that we need to talk about is what is a logarithm. So recall back to when we have done any of our other types of functions. So with our quadratics, we had x squared, and we had the inverse of an x squared is taking the square root. We also learned about in our last chapter the other types of roots that we have. So a fourth root undoes raising something to the third power. Okay, we also know that subtracting something undoes adding something, and they are inverses of one another. The problem that we run into is that, remember, with our exponentials, our exponent is our variable. And before now, we don't have a way to undo that. We can't take the x root of something. That doesn't make any sense. So we have to have some sort of other operation or some sort of other function that is our inverse. And that's where our logarithms come into play. So in general, a logarithm is the inverse of an exponential. So if we were looking at this, so say we had something like y equals b to the x, and we wanted to take the inverse of that. Remember that we would switch our x and y. And then we would need to solve for y. But the problem is that because the y is in our exponent, we wouldn't have a way to do that until we get to logarithms. So our second step that we have here says log base b of x equals y if and only if b to the y power equals x. So this gives us a way to solve for our y and get it out of that exponent. And something that you're going to hear me repeat quite often is that logarithms equal exponents. So notice that when we are converting from our logarithmic form to our exponential form, or vice versa, that whatever is in my exponent, which in our case is the y, that it goes to the opposite side of our logarithm when we convert it to that log form. And so that's why I say logs equal exponents, is because it's kind of a handy way to remind ourselves which one goes where. And then over here on the right hand side, it's just kind of a short example. So remember, we've been dealing with, in our previous sections, our exponential functions. So we had something that looked like the blue graph. So y equals 2 to the x. And remember that if we were to switch our x and our y, it's going to give us our inverse. Okay, and remember we talked about how our inverse graph is going to be reflected over the y equals x line, which is going to be that green graph. But since we just talked about that we know that our logarithm is the inverse of our exponential, we know that that red graph is going to look very similar to what our logarithmic graphs are going to look like. So let's go ahead and practice a little bit converting from one to the other. So it says write each equation in exponential form. And remember my little tip that I told us was logarithms equal exponents. Okay? Now the way that we look at a logarithm or that we read it is we, on part A, would say log base 2 of 8 equals 3. And that's really important because the 2 is the base of our logarithm. It's not just like hanging out. It's not a 28. It's not log of 2. It's log base 2 of 8. And that base is really important because when we switch to exponential form, that's also going to be the base of our exponent. Okay? So the base of our log is the same base as our exponent. And then remember we said that our kind of trick or way to help us remember is that logarithms equal exponents. So notice that here my logarithm equals 3. So that means that 3 has to be my exponent. And then my 8 is going to go over to the other side. So that would be what A is in exponential form or with an exponent. Now on part B, we have something very similar. Just this time we have a fraction, and that's okay. So again, this would be log base 4 of 1 divided by 256 equals -4. Again, my base of my logarithm is going to become the base of my exponent. Logarithms equal exponents. So this time my log equals -4, so -4 is going to be my exponent. And then I'm going to move that 1 divided by 256 to the opposite side. And if we look at that kind of equation there, it makes sense because remember one of our exponent properties is that a negative exponent flips our fraction. And so we would get 1 divided by 4 to the 4th, and 4 to the 4th is 256. Now in our second part, it's basically asking us to be able to go the opposite way. Sometimes we're going to need things in exponential form. Sometimes we're going to need to have things in logarithmic form. But we're going to need to be able to convert between the two whenever we need a specific form. So here we have 15 to the 3rd power equals 3,375. So basically we're going to work our way backwards this time. So again, remember that my base of my exponent is going to be my base of my logarithm. So 15 is going to be our base for our logarithm. And then remember that logarithms equal exponents. So 3 is my exponent, so that's what my logarithm is going to equal. And then the 3,375 is what's going to be on the inside. And that would be part A in logarithmic form. Now looking at my next one, we have 4 to the 1/2 equals 2. Again, we want to put this in logarithmic form. The base of my exponent is going to be the base of my logarithm. Remember that logarithms equal exponents. This time my exponent is 1/2. So that's what I'm going to put on the other side. And then on the inside of my logarithm, I'm going to have a 2. And depending on the situation, we might have to convert between the two. And that's why it's important that we know how to do both. Now, like I said, our logarithmic graph is the inverse of our exponential graph. And so it is our exponential graph that has been reflected over that y equals x line. So with our exponential graph, it gets large really, really quickly. With our logarithmic graph, it's going to get bigger, but it does so really, really slowly. So notice that on the first part, we are increasing, but it's increasing rather slowly. Also realize that for our exponentials, remember that we had an asymptote on our y-axis. But now, because our logarithm is the inverse, we've switched all of our x's and y's, which means that we've also switched our asymptote from being on our x-axis to being on our y-axis. So we have an asymptote at x equals 0. So that means that my graph, recall, is getting closer and closer to my y-axis, but it will never quite reach it, okay? And this is going to be an important thing, because what that means is that I'm going to have a domain restriction. So remember, for my y equals b to the x, our domain was always all real numbers, and our range was y is greater than 0. And because, remember, we switch our domain and our range because we switch our x's and y's to find our inverse, that's going to flip for our logarithmic graph. So now my domain is going to be x is greater than 0, and my range is going to be the all real numbers. Okay, and then the second one, so just like with our exponentials, remember that when we had a base that was between 0 and 1, it was an exponential decay graph. Our second graph that we have on the right is what we would get if we took the inverse of a decay graph. So this first one would be a growth graph, and this second one is a decay graph. And notice that it tells us that b still has to be between 0 and 1, because remember, the base of our exponent becomes the base of our log.